Good evening, everyone. This is the NPTEL problem solving session for the course Introduction to Algorithms and Analysis. This is the session for week 10, and we'll start by, as usual, discussing what were the topics covered and then going through some of the problems similar to what you have in this week's assignment. And while solving those problems, we'll also discuss some of the theory to make the solution more clear. Right? So, the topics for this week's lecture that are covered in the lecture videos are correctness correctness of Bellman-Ford algorithm, application of Bellman-Ford, then discussion on all pair shortest path algorithms or the problem statement of it. Then there was a discussion of the Floyd-Warshall algorithm for finding the all pair shortest paths on a directed graph. And then there was a discussion of Johnson algorithm for graph reviewing. Okay, so let us start by taking some of the examples for the shortest path finding, and then we keep changing the problems to cover as much as we can. Right? So let's say we start by this. Consider the following graph. Right. So we have A connected to B with a weight of 4, and this is a directed graph. This is 5, this is G, and being the central node, it connects to all of these. 4, 8, 2. Right? And what we have been asked is if B is the source vertex, what is the minimum cost to reach F? Right? Is it 8? Is it 9? Is it 4? Or is it 6? Right? So what we need to do essentially, we need to find basically the shortest path that exists between B and F. So for these kind of problems, of course, we saw different algorithms, uh, and one of those was the Dijkstra's algorithm, right? And yeah, so since we have a directed graph that has weights also on the edges, what we can try to do is we can try to use Dijkstra's algorithm to find the shortest path, right? And let's just first write the pseudocode for Dijkstra's algorithm, right? So we have a source node and we initialize the distance per se of the source node to itself as 0, and then for each vertex except the source node, we initialize the distance as infinite, right? And these are the distances that we will be updating. Right now, what we want to know is what is the minimum cost to reach f, right? And that's what the Dijkstra's algorithm gives. Like, finally, we end up with the minimum cost of reaching any vertex starting from the uh, source vertex s, and those distances are saved in these variables d, right? So we initialize a set s as null, right? And we initialize our priority queue as the set of all the vertices, right? So we initialize it like this, but going forward, we keep updating it with the vertices that are remaining basically, right? So while the priority queue is not empty, we extract the vertex that has the minimum value, right, within the priority queue, right? And then we update the set S, right, this one, to mark U as visited, right? And then for each of the adjacent vertices of U, right, we uh, relax the distances with updation, right? If dv is greater than du plus the weight between u comma v, right? If the current value is higher and the new value with the current connection that we are checking is lower, then we update the value for du as du plus w u comma v. So of course, if we just had to solve this question, we could have eyeballed it also that yeah, starting with at b, we can just try to brute force the solution, right? That to how many ways, in how many ways I can reach from b to f, right? So from b I can go to g, or I can go to c. From g I can directly reach f, that is one way, or I can go to e and then go to f, That is another way, right? And then from C, I can go to G and then take from G, from E to F, right? And then from D to E, and then I could have taken this also, right? So if we consider all of these, we can clearly see that going from B to G, G to E, and then E to F is the solution with the least total weight, right? So the least distance. But what we are trying to do here, we are trying to apply a Dice's algorithm to get the same answer, right? Because in this case, the answer is, as we can see, 1 plus 4 plus 1, right? So 6. Right? So this is the minimum cost to reach F. But how do we use Dice's algorithm also to find this? Because this was just brute force solution that we did, right? So what we'll do is let's try to solve our original graph. Right? Let's bring it down. I'm keeping it here. Okay, so the priority queue is currently initialized like this, F, G, right? And our starting node is B, so B has the cost, the zero cost, and everything else has been assigned infinity. Okay, and S, so like at the first step, the minimum is B, of course. So we put B into S and then we look for the adjacent uh, nodes of B, right? And adjacent nodes of B are G and C, right? So now again, we see that is the value from B to G and B to C, right? If this condition is satisfied for G and C, right? So we will notice that it's true for both G and C, right? Because the current costs or the distances for G and C are infinite, right? And infinite is of course greater than the current distance of the node U, that is 0, and the weight, right? So for G it is 1, and then for C it is 2, right? And now since B has already been uh, analyzed, right? So the next term, right? So let's mark B as being already analyzed. So the next term that we are going to look at is G, right? Because that has the, again, the minimum distances between all the other values, right? So now we do the same for the adjacent vertices of G, right? And which are the adjacent vertices of G? Right? It is A, F, E, and D, right? So let us, I mean, I'll do both of these things together now. I'll check and update, right? So for A, it will be G plus the weight, right? So it will be 3. For F, it will be 9. For E, it will be 5. And then for D, it will be 3. Okay, and we then insert G also into S, right? And we mark G as visited, right? So now we look for the minimum again within Q, and that minimum now is C, right? So we put C inside S, right? And then we start looking for the adjacent vertices of C, right? Those are D and G, right? So let's check for D first, right? So is D of D, right? That is 3. Is it greater than 2 plus the weight 10, right? No. So we don't update anything for D, right? And similarly for G, right? D for G right now is 1, right? And D for C plus the weight between C and G right now is, so 2 plus the weight is 3, that is 5, right? So again, we do not update because the condition is not met, right? So nothing gets updated, but now C has been marked as visited. Okay. Now in the next iteration, we take A because we can take anything between A and D. Right, let's take A. So for A, it's B and F, right? So let's check for both B and F. So for B, it is currently 0, right? And of course, 3 plus 4 is greater than, so 7 is greater than 0, so we should not update B, and we won't. And for F, it is currently 9, right? So D of F right now is 9, right? But if we reach F through A, right, and that is D of A plus W A comma F, right? That is D of A is 3 and W A comma F is 5, that is 8. And 9 is greater than 8, so the new weight 8 is an improvement over the last one, right? So we have found a path that can make us reach F in a lesser distance, right? But it is again not optimal because it is not converged. Okay, so we have updated for F and we mark A as visited, right? So the next one is D, right? We take D, we put it into S, right? And then we look at the adjacent values of D, adjacent vertices of D, that is only E, right? And again, the current value of E is 5 and current value of D plus the weight is 9, that is higher. So we won't update it. We'll just mark D as visited. Right. So now we'll look at F. No, E. Sorry. We'll look at E. Right. We look at E and the only outgoing vertex for E or the only adjacent vertex for E is F. Right. And D for F, right, when we are looking at E, so currently it is 8 and D of E plus the weight between E comma F is 5 plus 1, that is 6, right? So it is lesser than the current value. So we update f as 6, and then we mark e as visited, right? So now we are left with the last value, last vertex, that is f, and so we check f, and now f has no outgoing corrections, right? So we do not update anything, but we just mark f as also visited, right? So this is now, right, the optimal distances, right? So if I write this, right, d as 3, 0, 2, 3, 5, 6, 1. Okay, so these are the optimal distances or the minimum distance to go starting at B to any of the vertices, right? And the vertices here are A, B, C, D, E, F, G. And the original question was, what is the minimum cost to reach F, right? And by this analysis, the minimum cost to reach F is 6, right? And that is what we like got intuitively also, right? When we were just trying to find the answer using brute force. Right? But now we analyze the complete graph using Dijkstra's algorithm, and we got the same answer. So everything checks out. Okay, so now one more thing that I think I should just discuss here is that right now what we end up with is just the distance to go, right? What will be the minimum distance to go from vertex source to vertex goal? But we don't have the shortest path, right? We don't have any information because we did not save that information while analyzing the graph, right? And we could easily do that as well by maintaining another list called P that contains the parents of all the vertices, right? And basically we keep updating parents when we update the values for each one, right? And we start with, let's say, nil for each one, right? And as we keep updating the values here, right, we keep updating the parents also. So let's do that with one more example. So in the given graph, identify the shortest path having minimum cost to reach vertex E if A is the source vertex. Right? And the graph that we have to analyze is this. A, B, C. right? And the options that we have are A, B, E, A, C, E, C, A, C, D, E, or A, C, D, B, E, right? So our source vertex is A, and our goal vertex is E. Okay, now what is the shortest path? So again, we'll use Dijestra's algorithm, right? So the priority queue, again, we populate with all the vertices A, B, C, D, E, and the D values for each of them. Right? For A, it is 0, and for all others, we initialize as infinity. And as I was discussing, we also maintain one more array, right? That we use to basically track the parents of each vertex, right? And how we update parents, we'll go through in this example, right? But we initialize it. Let's say for A, we give, let's say we keep it empty for now, right? For all values, it's just none. So for A, B, C, D, E, right? And this array P contains the parents in the shortest path, right? For every vertex. And we'll see like how we get there. So we start by uh, taking A, right? So we put A into the matrix S or the array S, and then we look at the vertices or the adjacent vertices of A that are B and C, right? So uh, again, the condition that we have here in Dijkstra's, it's valid, it's true for both B and C, so we update it. So for B, it becomes 1 because 0 plus 1, and then for C, it becomes 3, right? And then in the next iteration, we take B, right? And now we check for the vertices of B, and that is only G here. Oh, sorry, that is only E here, right? So the value of E again will be updated to 7. Okay, now before we chose the value of B, we update the parent of B as A here, and here parent of C also as A, and parent of E in the second iteration when we updated this E to be, the value of E to be 7, we update this to be B. Okay, that basically we put the we put U here, right? We put U here if this value is true, right? So we can like augment this. If this is true, then do this and like update the parent as U. Right now we can just do this small modification in Dijkstra and we have now the shortest path algorithm. Right, so we have updated B. Now we check for again the minimum value that is for C right now, right? So we take C, we put C here in S, and then checking for what adjacent vertices of C, so E and D, right? So for D, it will be 3 plus 4, right? So 7, and since it has been updated, so this goes here C, and then for E, right? So our U is C right now, right? And we are checking for D of E. Right now it is 7, right? And D of C plus the weight between C and E is 3 plus 2, that is 5, right? So it's lesser than 7, so we need to update, right? So for E, we update this as 5, and since now this condition was true, we update the parent here also for E, right? Now in the next iteration, we check E, right? And E has no outgoing adjacent vertices, so we just mark E as visited and do nothing. And then for D, right? For D, the outgoing vertices are again E and B, right? So we check if D leads to a shorter path to B or to E, right? So we check that the current value for B is 1, right? And the current value for D itself is 7, and we only have positive weights, so B will not be updated. And same thing for E, right? So our algorithm is done here, right? So one thing that we know is that the minimum cost to go from A to E is 5, right? That we can see here, right? But that's not what we wanted. What we wanted was the shortest path, right? And for the shortest path, right, what we do is we basically start at our goal vertex, and then we keep appending the parent of the vertex and then the parent of the parent, right? Unless we hit null, right? So uh, let's say we wanted to write the shortest path. Let's say we denote it as L, right? So we initiate or we initialize L as an empty set, right? So if we want to write it in algorithmic form, and while, and we say that V is the goal vertex, right? And we say that while V is not null, right? Or is not an empty element. Let's say this is empty here, so that we maintain difference, right? So we keep appending the parent of V, right, into L, and then we update V as the parent so that we look for its parent in the next iteration, right? And if we follow this with this parent array that we have, right? So our G is E, right? And then, yeah, so in the end, we do L dot reverse, right? Because we are again backtracking the solution, right? So since G is E, so we go to E, right? So the first one E, and then the parent of E is C, right? So C, and then the parent of C is A, so A, and then the parent of A is phi, right? So we end here, right? And then we reverse it, so we get A, C, E, right? So this is the shortest path that has the minimum cost to go, right? That we have calculated here. And this we can verify also from the graph that if one goes from A to C, that has a cost 3, and then from C to E, that has a cost 2, that is indeed the shortest path to go from A to E, right? Because all the other paths have a greater cost. For example, from A to B, and then from B to E, the total cost is 7. From A to D, A to C, C to D, and then from D to E, the total cost is 8. So we can try any of the different possible paths, but we have the shortest one now. Right? So this is some of the example applications of the Dijkstra's algorithm, and one small modification to then get the shortest path as well. So let's go on to the next example. So let's say we say consider the following directed graph, and the graph is this: 1, 2, 3, 8, 1, 9, from 3 to 1, 4. Right? What we want to do is, using Floyd-Warshall algorithm, find the matrix that represents the shortest path distance between every pair of vertices. And I'm not going to write the options for this because, again, it will just be uh, a waste of time. So we'll directly find the matrix, right? And uh, so clearly, this shows that what we were doing till now, right? The Dijkstra's algorithm was for finding the minimum cost to goes from a single source, right? From a single vertex, right? But what we want to do now is we want to find the all source, uh, right? So formally, I think in lecture notes, it's called the all pairs shortest path, right? Shortest path. So let's try to solve it. And before solving it, again, since we have been told to use Floyd-Warshall's algorithm, we will revisit Floyd-Warshall's algorithm. Okay, so what we essentially do in Floyd-Warshall's algorithm is we again maintain, instead of an array, we maintain a matrix for the shortest distance dij, right, between any two. Okay, between any two vertices, right? So earlier we were just uh, we just had one index because we only had an array. Now we have a 2D matrix, so we have two indices I and j, right? And what Floyd-Warshall does essentially is uh, in the first iteration, right? We initialize this matrix for with 0 for all the diagonal entries, or we can also say that this is equivalent to the distance from vertex to itself, right? So basically, Floyd-Warshall is equivalent to applying Dijkstra for each vertex, right? So again, we can just apply Dijkstra for each vertex, and we'll end up with essentially what we would end up with Floyd-Warshall algorithm, because that's what it is. Okay, so we start with infinity if I is not equal to j, right? And then for all the other vertices, right, that are adjacent to vertex I, we update, or we can simply use the same notation as Dijkstra's, that for all k, do for I 1 to n, for j 1 to n, right? This is just pseudocode that we are trying to write for Floyd-Warshall. If Cij, or uh, we have called it Dij, is greater than Dik plus Dkj, right? Then we update. Right? So Dij essentially up, is updated with the new smaller value Dkj. So if we were to apply this algorithm for this graph, right? So we have four vertices. So our matrix D will be a 4 cross 4 matrix with these values initially. Okay, so we start with k equal to 1, and then we go through the entire array, right? And then we go for k equal to 2, and then we go through the entire array. Okay, so uh, for k equal to 1, right, what do we have? Or let's say we just uh, so d let's say 1 1 is right now 0, right? So that again cannot be changed. So we go to d12, that is infinity, and d12 is it, right? So k is 1, right? So d11 plus d12. Okay, so is it greater, right? Or we can uh, let's say for from 1 to 2, right? It is 8, so we update it as 8, and from 1 we can only go like 2 and 4, right? Not 3 right now, so we update it as 1, right? And then for the same k in the next row, right? When let's say hypothetically we were starting from 2, right? So we test for 3, right? We can only test for 3, so we update 3 as 1, and similarly for the next we go 4, and then we go 12, because now this value infinity is less than, right? So d32 is infinity, and d31 plus d12, right? That is 4 plus 8, that is 12. So 12 is less than infinity, right? So we update this value as 12. Okay. So similarly, we have 5 here. Okay, so let's, yeah, because this is for k equal to 1. So this is anyways gonna happen. So d3 4 is, let's say, currently infinity, and d31 plus d14 is 5. So we update this 5. Coming down further on the last row, uh, d41 is infinity right now, and d41 plus d14, right? So it doesn't make sense because it's infinity, so we leave it as it is. And then d42 also is infinity, but d41 plus d12. Okay, so d41 right now is infinity, and d12 doesn't matter, it's 8, but it will still be infinity, right? So when we go through different values of k, right, we'll keep updating these values, right? So if I had to just write the time evolution of these. So after first iteration, it will be this matrix. After second iteration, right, for k equal to 2, it will be 0, 1, infinity, right, and then 4, 12, 0, 5, 80, 2, 9, 0, right, and then we go for 2, right, so for the next element, that is vertex 2, right, so when we go searching for that, we end up with this 1, infinity, and like for getting all of these matrices, we are just applying this. We are checking, like for all k starting from 1 to n, we are doing one pass of the matrix, and at every element we are checking this condition, and if this condition is true, then we are updating, right? That's all we are doing here. 20, 2, 3, 0. When we look at 3, right, vertex 3, it will be 0, 8, 9, 1, 5, 0, 1, 6, 4, 12, 0, 5, 7, 2, 3, 0. And for the last, uh, in the last iteration, these values will be updated to 3, 4, 1, 5, 0, 1, 6, 4, 7, 0, 5, and 7, 2, 3, 0. So this is the final all pair minimum cost to go matrix that we are looking for. Okay, so let's just take one more example. What is the recurrence relation of Floyd Warshall's algorithm? Right? What is the basically all pair equivalent of the Dijestra's recurrence relation for Floyd Warshall? So we know that the recurrence relation is Cij at kth, for the kth vertex, is the one that minimizes, right? So either it is the existing distance or the cost or whatever we want to call it, or it is the updated, right, or the relaxed cost in the new search space, right? So again, we are looking for the minimum cost. Okay, and yeah, again, this is not j, this is k, because we are relaxing it with k. So yeah, this is the recurrence relation that we even used in the problem above. Okay, so I think this is more than enough for what you need to be able to solve this week's assignment. Uh, I'll stop the meeting now. Thank you.